Hello and welcome to iitiansgateclasses once again. So we are continuing with binary search tree. So yesterday I explained the structure of binary search tree where at each node, the left subtree is basically less than the current node and the right subtree is greater than the current node. Okay, we have seen that, right? We have constructed one binary search tree. For example, it will look like one. I'm drawing one example of the binary search tree. So it will look like this. If the root node is 100, all the nodes on the left side, all the nodes, the left subtree will be less than 100. Okay, will be less than 100. For example, if 50 here. Similarly, this same condition applies for 50 also. On the all the node on the left side will be less than 50. Okay, so we will see that. Okay, 20 here, 10 here, 30 here. See, 10, 20, 30 all are less than 50. Similarly, it goes for 20 also. 10 is less than 20 and 30 is greater than 20, right? Similarly, on the right side, we have all the nodes will be greater than 70. Okay, so we have 60 here and 80 here. Okay, 80 is greater than 70. So this follows up for all the nodes. And this makes the finding on the nodes easier, right? So 130, 110, and 140 here, something like this. Okay, so this is one example of binary search tree. Binary search tree. Okay, it is a binary tree with this constraint that I explained just now. Okay, so this is binary search tree. Now, what is the property of the binary search tree? That if we do the in-order traversal, so let's do the in-order traversal of this binary tree. What is the in-order traversal? I will write program also for in-order, pre-order, and post-order traversal. Traverse means that we are going for each node and we are printing it, or basically we are like starting from the root, we will be traveling all the nodes. Okay, we are going to touch each node because we have the starting pointer of the, or you can say root pointer of the tree only. From that, recursively, we are going to go for each node. Okay, so that is traversing. Traversing. So we are going to do traversing. Let's do in-order traversing. In-order traversing. What is in-order traversing? In-order traversing is print. Okay. Go to left first. Then root. After that, go like print root. After that, go to right. Okay. So this is also called left, root, right. In order, you can consider in order where root falls between left and right. Okay, so this is in order. So let's do the in order traversing. First, let me write the program for in order. And we are given with the struct node star root. Okay. Now we first have to go to the left. We say that if root equal null, we will return. Because root is null, we cannot go left or right or print anything, right? So if we say that if root left equal null and root right equal null, just print it. We are printing. Traversing means we are basically going for all the nodes one by one recursively. So we are printing it. Print the root data. Okay, print the root data because we are at leaf node. And return. Don't do anything, just return. So this is for null check and this is for leaf node check. Okay, so we are at leaf node and we have to go back. If these two are not the condition, what to do? First, go to the left node. Okay, so we will call in order again. and we are passing root left subtree. So we are basically we are going for the left subtree here. Then we are printing the current node, which is root data. It is not going to print 2 times because we are returning here. In this condition, we are returning. If we are at leaf node, we are returning. Else we will do in order root right. Okay. So this will first recursively go into the left subtree and try to print the leftmost. Then it will print the root node. Then it will go for the right subtree. So these 3 steps are quite important. See this order. In order, go to left, then print the current node, then go to right. Okay. This is what we are doing in order. So this is called left, root, right. Okay, this is in order. Left, root, right is in order. So let's do the same thing here. Let me erase this thing. So on the same tree, we are doing the Inorder Traversal. And you will find something. Why am I doing Inorder Traversal first? It's because of one property of binary tree. Let's see what is Inorder Traversal here. So we are at the root now. We'll pass this pointer. And both of these conditions, this is null check. This is leaf node check. And if those 2 conditions are not satisfied, we are returning in these 2 conditions, then we are going for recursively in the left subtree and the right subtree in this order: left, then print root, then go into the right subtree. Okay, so here this is not null. So we will go here in the left one, right? Because we have called this function on the left node. Again, this is not null, and it's this is not a leaf node. Then go to this node. We are going directly in the left node, right? So what is the in order calling? We are calling like this. We are going like this, right? We are going like this. Then here 20 is also not null, and it is not the leaf node. We will go here. Now 10 is the leaf node, so we will print 10 here. We will print 10 and we'll return back to the 20. We'll return back to 20. Okay, now this program has a caveat that yeah, no, there's no caveat. So we have gone to the left subtree and we have printed the left subtree. Here we are saying that we have printed the left subtree, not the left node only. We have printed the left subtree. Then we are printing the current node. Current node is 20. Let's print 20. Then we are going to the right subtree, which is 30 here. Okay, so we will print 30. After all these 3 steps are done, after that all these 3 steps are done, we are going back to parent. Okay, here we are going back to the parent. Here we are going back to the parent calling function, right? So here also, after printing 20, after printing 30, we are going to the parent. Then we are going 50. So we'll print 50 here. The similar fashion, we will go to 70. Then we will go to 60 and we will print 60. Once we come back from the 60, we will print 70. See, once we come back from the left subtree, this is left subtree, we are printing the current node. Then we are printing right subtree. So this is the order. Go to the left subtree, print all the nodes, then print the current node, and then go to the right subtree. That is our scenario here. So we come back from the left subtree, we print the current node, then we will go to the left subtree, which is 80. Then we go back from here to here, then here to here to 50. Now the whole left subtree is printed. This whole left subtree is printed. Then we will print 100. Similarly, Once the 100 is printed, it will go to the right subtree. For 130, we will go to the left subtree, which is 110. Once we come back from the left subtree, we will print 130. Then we go to the right subtree, which is 140. So if you see, if we try to print in order, this is in order traversal of binary BST, binary search tree, BST, right? Now here you can see one more property. So if I check 50, in the in-order traversal of 50, what is its predecessor? This is predecessor and this is successor. In the in-order traversal of a tree, if we pick one node 50, what is it? Predecessor. Its predecessor is 30 and its successor is 60. So the one conclusion from in-order traversal is in-order traversal of binary search tree is always sorted. Okay, you can see here, right? 10, 20, 30, 50, 60, 70, 80, 100, 110, 130, and 40. It's sorted. So all elements are sorted. So this is one conclusion. The second conclusion is the second analysis that you can do by looking at this in-order traversal, that if you pick any node, any value, like 50 we have picked randomly, the predecessor in the in-order traversal, it lies on the left and then the rightmost part. For example, let me build this same tree again. 100, and we have 50 here, 20, 10, 30, what was it? 70, 60, 80, 70, 60, 80, 130, 110, 140. Okay, so what is the in-order traversal? 10, 20, 30, 50, 60, 70, 80, 100, 110, 130, 140. Okay, so this is in-order traversal. Now, if you pick 100 here, who is the predecessor of 100 in order traversal? We are talking about in-order traversal only, right? So what is the element that lies just before 100? So it is basically go to the left, then go to the rightmost element. That's what lies here. What about this one? What lies on the right side of 100? Go to the right one time, only one time, then go to the leftmost node. So let's do one thing. Let's like modify this tree, add more nodes here to make you understand better. Okay. So suppose here we have more nodes. Okay. So I will have 105 here and 120 here. Okay, 120 here. Then here I will have more nodes. I have 101 here and 107 here. Okay, so this is again a valid BST, right? Now do the in-order traversal again. Till here it will be the same because we haven't touched the left subtree and the root. After that, we will have the right subtree. Okay, we will have the right subtree. Let's see what is the traversal after that. It will be 101, 105, 107, 110, 120, 130, and 140. This will be the remaining Inorder traversal. Now, in the Inorder traversal, what lies on the right side? Exactly one step on the right side. This is called, so this is called predecessor. Here, if you see, this is called predecessor. Predecessor. This is called successor. Okay. So in Inorder traversal, what is the predecessor of 100? Take one left and then take all rights and reach to the leaf node. Similarly, in case of successor, take one right and take all the lefts and reach to the leaf node. So this is the one. Okay. So right now we know that what is the successor and predecessor in Inorder traversal for any node, For example, if we talk about 130, what is the predecessor of 130? Take one left and then take all the rights. Now you can see 120 is the predecessor. Okay, 120 is the predecessor. And who is the successor of 130? Take one right. And we have reached to the leaf node, so we cannot take any left or right, any more left or right. So 140 is the successor of 130. Right? Now we are talking about, once we do the Inorder traversal, which value or which node lies on the left side in Inorder traversal. Take one left and then all the rights, you will reach to the predecessor. Take one right and take all the left, you will reach to the successor. Now this is very important, because if you want to delete something, in the binary search tree, for example, if you deleted 100 from here, you will replace this 100 either from the successor or predecessor. For example, you can pick any one of them. So I have picked 80 here. So I will pick 80. I will replace it here by deleting from here. So I replaced the 100 from 180, and our tree structure won't change. Our tree will remain same as it is. It will follow the constraint that for every node, the left subtree should be less than the node and the right subtree should be greater than the node. So it will remain same. Okay. You can check. Okay. Let's do the Inorder traversal. What we did, we replaced 100 with its predecessor. You can replace it with successor also. It won't change anything. It's just the same thing. You can follow any of the approach. Okay. So right now let's do the Inorder traversal. Inorder traversal for this tree is 10, 20, 30, 50, 60, 70, 80. We have removed 80 and we have pushed 80 here, right? 80, 101, and we have done 105, 107, 110, 120, 130, and 140. See, now the structure is same. Again, once we do the Inorder traversal, we will get a sorted array or sorted elements, and the deletion is successful. Okay. So if you would have replaced instead of 80, if you would have replaced 100 with 101, it will remain same. Right? The Inorder traversal will change. So let's do that thing also. Let's try that thing also. First, let me try to restore the original tree. So original tree is 100 here, 80 here, 105 here, 101 here. Now we want to delete 100. Delete 100. Find out its successor, which is 101. So we delete 101 from here and replace it here. Now, what is the Inorder traversal? The Inorder traversal will change like this. After 70, we will have 80, 101, then 105, 107, 110, 120, 130, and 140. See, the Inorder Traversal is same again. And we have seen that the root is 101. Okay. So this is what Inorder Traversal. Inorder Traversal. So remember the properties of Inorder Traversal in BST, binary search tree. That Inorder Traversal will always be sorted. Okay. We will always get sorted elements. And the deletion is easy. Once we do the Inorder Traversal, just find out the predecessor and successor of the element which you want to delete and replace with that predecessor or successor, the node that you want to delete. It's easy, right? Now, let's move on to the next part, where we want to insert something. If you want to insert something in the tree, for example, I want to insert like 90 here. Where will I insert 90? Finding out the position in the binary search tree is the same thing as finding out an element, right? If I want to insert 90 here, let me do one thing. Now here we have deleted 100 from the root. Okay. We have 101 here. And now we want to insert 90. We will check root. 90 is less than 101, so it will fall in this subtree. We will never check right subtree now. Now it is greater than 50, so it will fall in the right subtree of 50. We will never check this one. We will never check this one. And it is greater than 70, so it will fall it will fall on the right side of the 70, and it is greater than 80, so 90 will fall here. Now, if I want to insert 55, how will I insert? So inserting 90 was easy because that was a leaf node. That turned out to be a leaf node. Okay. Now, if I want to insert 55, what will I do? If I want to insert 55, what will I do? I'll check it is less than 101. We'll go here. It is greater than 50. It is basically greater than 50, so we'll go here. It is less than 70. It is less than 70, so we'll go here. And it is less than 60 also, so we'll insert here 55. Sorry. So once we do the insertion, if you check now, the insertion always happens at the leaf node. You can try it. Once you reach to a proper leaf node, whose children, the new node will be a part of one of the leaf node children. Okay, it will become a child of any of the leaf node by searching mechanism, right? Now we have seen the skewed tree also, right? The skewed tree, skewed binary tree, where this node is greater than this node, this node is greater than this node, this node is greater than this node. So if we pick only the skewed tree, it may happen that in binary search tree we have the skewed tree. So insertion will take order of n time because finding out the correct position may take time, right? So for example, if our incoming node is less than if our incoming nodes, for example, if this is 60, if you want to insert 50 here, right? So in that case, and this is 40. We'll check that, okay, 50 is greater than 60, go here. And 50 is less than 60, so we'll insert 50 here. And we may reach to like the last node also, right? So the insertion can take order of n time maximum in worst case. In worst case, the insertion can take order of n time in binary search tree, right? And the deletion can also take order of n time, right? Because if you want to delete something, right, then what happens? You will replace it with the predecessor or successor. So it may take order of n time, right? So this is the time complexity of deletion as well as insertion. Okay. Why deletion take order of n time? Because to find predecessor or successor may take order of n in case of skewed tree. In case of skewed tree, right? So that may happen. Now let's see what is the solution for this thing. We want to avoid this like one-sided tree, because a node can have at max 2 subtree, like 2 children. So why can't we make 2 children mandatory? Okay, so for that we have Avl tree. Avl tree. It is a binary search tree, but balanced. Balanced. What does it mean by balanced? So at each node, remember this formula, mode of left subtree height. Okay, that is why I made you calculate height. I explained what is a height. If you don't remember what is the height of a node, you can go back and check the program as well as the explanation. Like 2 lectures back, I explained what is the height of a tree. So left subtree height minus right subtree height can only be 0 or 1. I have taken modulus, right? Modulus. So the height of left subtree and right subtree can only be 0 or 1. So if we talk about Avl tree, okay, let's talk about Avl tree. The first thing is it should be binary search tree. What is the binary search tree? Where each node, all the left subtree node are basically less than the current node, and all the right subtree node are greater than current node. Okay, as well as it should be balanced. Plus it is called what is balancing factor? Balanced factor. It could be -1, 0 or 1. Balance factor is basically left subtree height minus right subtree height. So this is the balance factor for each node. So the balance factor should be either -1, 0 or 1. Okay, the balance factor always should be -1, 0 or 1. Okay, where the left subtree height minus right subtree height should always be -1, 0 or 1. So let's see some example. For example, if this is a tree, like we have 20, 10, and 30. So what is the height of the left subtree here? It is 0. What is the height of right subtree? It is 0. If you subtract them, the balance factor, BF, I am saying balance factor, okay? So balance factor here is 0. Here also the left subtree height is 0, right subtree height is 0, and the balance factor here is 0. And the height of left subtree is 1 here, it is 1 here, so the balance factor is 0 again. So this is properly balanced. It is either -1, 0 or 1. So this is satisfied. Now let's talk about this thing. Here the balance factor is 0. Here the balance factor is -1. Why -1? Not -1, sorry, +1. Why +1? Because left subtree height is 1 and right subtree height is 0. So it is 1. Similarly, for 30, the left subtree height is 2. The right subtree height is 0. So it is 2 minus 0 equal to 2. Now, here at this node, this is imbalanced. This is imbalanced. At this node, this is balanced because balance factor is 0. At this node, this is balanced because balance factor is 1. Here it is 2. The balance factor is 2. So that is why it's imbalanced. Similarly, if we talk about like something like this, 20, 30, here the balance factor is 0. Left and right height is 0. Here the left height is 0 and right height is 1 actually. 1. See, it's 1. There is exactly one node here. So it's -1. The left and right is basically 0, -2. The height of this node is, from the left subtree height is 2. Okay, left subtree height is 2. That is a 0 - 2 equal to -2. This is imbalanced. Let's see some more complicated example, like something like this. Okay, 50, and we have 20 here, 10 here, and 70 and 80 here. Now, is this tree? Pause the video and try to calculate the balance factor for each node, and try to figure out whether this tree is imbalanced or not. I'm writing the balance factor for each node. Okay, so 0 here, 1 here, 0 here, -1 here. Okay, now height of the right subtree here is 2, height of the left subtree is 2, and it is 0 here. So see, at each node, it is either 0 or -1 or 1. So this is a AVL tree, valid AVL tree, valid AVL tree. Okay, we don't have to worry about it. Now let's write one more example, 50 and 30 here, 20 here, 10 here, and we have nothing here. Here we have like 70, 60, 80. Okay, so this is our tree now. So what is the balance factor here? Now let's calculate it. It's 0 for this node, 1 for this node, and 2 for this node. 0 for this node, 0 for this node, 0 for this node. Okay, and 1 for this node. Why 1? Height of this tree, like see, 1, 2, 3. 3 minus 1 and 2, or 1 or 2. 3 minus 2 equal to 1, right? So it's imbalanced at this node. It's imbalanced at this node. Still, it's imbalanced. So it is not a valid AVL tree. So how to make a imbalanced AVL tree balanced? Let's see some scenarios. We will cover all the scenarios where a tree can be imbalanced. Okay. Now there is one problem which is called RR problem. RR problem. Where at any node, I'm not talking about root node. Okay. I am writing down a fraction of the tree, right? So if at any node, our tree will look like this. Okay. So this is called right RR problem. Okay. So if we have the balance factor in -2, it means we have RR problem. So to solve the RR problem, we do left rotation. Okay, left rotation. In the left rotation, we will rotate it like this on the left side. Okay, so you can consider that this is a hinge. This is a hinge, and we are rotating it on this hinge. So it will look like this. After left rotation, it will look like this: 20, 10, and 30. Okay. Now this left rotation seems simple when we don't have any children here. Right? What happens if we have children here? What happens if we have a children here? Here we have A, here we have B, C, and D. This A, B, C, D represent what? This A, B, C, D represent actually subtrees. Okay, subtrees. A, B, C, D are subtree. Okay, so I'm not printing the whole tree like this structure here. I'm just printing the subtree. The subtree structure won't change, but its connection to the parent will change. Its connection to the parent. Right now, once we do the rotation, this left rotation, what will happen after that? Okay, once we do the left rotation, what will happen after that? Let's see. So now, once the 20 go up, like up, okay, this A 20 have now 20 had a left children. 20 had a left subtree B. But here 20 had 10. So what will happen to B? B will come here. Okay. And the left children of 10 will remain same, A. And left and right children of C 30 will remain same. Note this down. Don't try to mug it up. Okay. Try to think it through. Try to think it logically. That what happened? That the left subtree here, all the node in B, in this subtree B, are less than 20. We know that. Okay, all the node in B are less than 20. Right? So once the rotation happens, after rotation, the B should always be on the left side of 20. Now it is on the left side of 20. Okay, see, on the left side of 20. On the left side of 20. B is on the left side of 20. Okay, in the left subtree. And how can be this possible? Only when it is right children of 10. So why is it the right child of 10? Because the B in the beginning, in the original tree, B was actually on the right side of 10. B is in original tree. In original tree, B was on right side of 10. And it's still on the right side of 10. Okay. So this is the scenario. Now you know that in linked list and doubly linked list and in tree, we have seen many pointer change programs. Okay. So we can construct a program out of it to do the left rotation. First, we identify where is the problem. Here is the problem. Here the problem lies. Where the imbalancing happened. After this, we will pick two nodes. Okay. It's -2. It means that the below two nodes are skewed. It has some skewed structure to it. So to make it balance, we will do the left rotation. Okay. And after that, we will change the parent of B to 10. Okay. I hope this clears you. Okay, let me write down this properly. So what we had initially, 10, 20, 30. So it is imbalanced here, -2 here. And we did the left rotation. This is our problem using left rotation. Right, you can say right problem. So right problem can be solved using left rotation. What is left rotation? Rotate it like this. Okay, so we did 20, 10, and 30. So wherever, for example, here was some link here, So that link was initially connected to 10. Now it's connected to 20. The same link is connected to 20. Now let's talk about the children, or you can say child subtree. A here, B here, C and D here. So this A will remain on the left of 10. It was on the left of 10. This B will remain on the right of 10 because in the original tree it was on the right of 10. Okay, it was on the right of 10. And B will remain on the left of 20. Okay, so it was indirectly, it's on the left of 20. In the initial tree also it was on the left of 20. C and D will remain same. So this is left rotation. Similarly, we will do right for LL problem. So now we are going to talk about LL problem. Now you can pause the video and try to write down the problem as well as solution. Okay, so I'm writing down the problem. So if our problem look like this, there is some link to 30 is linked to some other parent node. We don't care about it because the problem lies at 30. Here we have balancing factor 0, for example. Here we have balancing factor 1. Here we have balancing factor 2. So if problem lies on this node, okay, specifically on this node, on 30, and 30 is connected to some parent node. So this is left problem. This can be solved using right rotation. Right rotation. So we will rotate it like this, in this direction. Okay. So after right rotation, our tree will look like this. So wherever the 30 was connected, the 20 will connect on the same node. 30 was, we are considering 30 was child of some node, and 20 will replace it. Now what will happen to the children? Or you can say child subtree. Here, if we have A here, B here, C and D here. Okay, so the C and D will remain at the same position. The B will come here and A will come here. Okay, so this preserve or BST constraints as well as the balancing factor is applied. Now it's the balancing factor here is 0. Okay, 0 or 1. 0 or 1. 0, 1 or minus 1. So these two problems are easy. Left rotation and right rotation. Now let's talk about LR, left right problem. I hope you can visualize the problem. Okay, I'm not constructing the whole tree. Using some example, I will try to explain, but this problem, I hope you understand that what is the problem. Okay, here, that the balancing factor, what is balancing factor? Based on that balancing factor, we can visualize it, that what is happening, what is the problem? The balance tree is going out of the balance. So if our tree will look like this, 30, 10, and 20. So here, if balance factor is 0, here is the balance factor is -1. But this lies on the left side. So height of the left subtree here is what? For example, the height of the left subtree here is 2 or some value, okay, which is less than its children here, which is less than its children. Okay, so what's happening here is this connection, or you can say this link, is also part of the height of left subtree. In case of 30, we am talking. Okay, so here it is 2. It's imbalanced, right? The height is 1 and 2. Left, because 20 also lies on the left side, right? On the left side of 30. That is why it's imbalanced. Now it's LR problem. L and R. LR problem. So it takes 2 steps to solve it. Step one is do, its name is LR, right? So we will do left rotation first on this node. On 10, we will do left rotation. We'll do left rotation. Okay, so let me clearly write down this tree. In LR, we will do left rotation first, then we will do right rotation. So our nodes are something like 30, 10, and 20. So we are doing left rotation here. After left rotation, it will look like this: 30, 20, and 10. Once we did the left rotation, we will do right rotation. So now you can see it's LL problem, right? It's LL. So it is same as this problem, LL problem. So we will do right rotation. In right rotation, it will be 20 will become the hinge, and we rotate on this. So it will become 20 here, 10 here, and 30 here. Now let's try to write its children. So we have A here, some tree, some subtree is here. It could be null also. B here, C here, and D here. And it is child of some parent node. So now after doing this rotation, what will happen? After doing the right rotation, this left rotation, the first step, after performing the first step, how the child will be attached to the parent. This A will remain here. Okay, we will never touch this A because this part we are not touching in the left rotation. We are just rotating these two nodes and its children. Okay, and B will remain here, C will come here, and D will remain here. Now you can see what happened. On the left side, previously we had C. On the left side of 20, previously we had C. After rotation, on the left side, 10 will come. So the C has to become the right children of 20, the right children of 20, because in the original tree, the C lies on the right side of 10 and on the left side of 20. So that is why C has to become right child of 20. So these A, B, C, D are basically subtrees. Once we do this rotation, we will follow the same concept like this. We will follow the same concept. So this is a right rotation. Right rotation. Okay. So after right rotation, what will happen? Okay, the D will come here. A will remain here. B will remain here, and C will remain here. Okay. Similarly, let's solve the next problem, which is RL problem. So we have structure like in case of RL, we have structure like 10, 30, and 20. Here we have -2. Okay. So we will do first right rotation. RL problem, to solve the RL problem, we will do right rotation first, then left rotation. As the name suggests, okay? So the right rotation will happen. The right rotation will happen here. Okay, here. This is right rotation. So it will look like 10, 20, and 30. After that, we will do a left rotation. So the left rotation will happen here. 20, 10, 30. Let's draw the children for we want to look at the bigger picture where they may have some child node. Okay, so here we have A, B, C, and D. So after this rotation, the D will come here. B will come here. Here we have C, and A will remain at the same position. Once we do this rotation, A will come here, C will come here, D will come here, and B will come here. Okay. So this is to solve RL problem. Now, how can imbalancing happen? How can imbalancing happen? Imbalancing can happen once we try to insert some node in the tree, okay, or we try to remove some node from the tree. The insertion and deletion will happen same as binary search tree. So we have seen that in case of deletion, we will look for the predecessor or in-order predecessor or in-order successor. And I've already told you what was in-order predecessor and what was in-order successor. So we look for in order predecessor or in order successor. We'll try to replace it to the given node which we want to delete. And after deletion, imbalancing can happen, and we balance it out using this thing. So let's see some example here. So consider a very big Avl tree. Okay, so it look like this: 100, 50 here, 200 here, 30, 70, 20, 40, 10, 45, 80, and 90. Now at 200, we have 150 to 10, 120, 170, 110, 130, 105, 115, 140 here. Here we have 160, 180, and on the right side of 160 we have 166. Here we have 205, 220, 209 here, 215, 225, and 230. Okay. So this is the tree. Right now, this is a Avl tree. You can check the Avl tree, right? Very easily. That here, this is at 0, 0. The balancing factor, I'm writing 0, 0, 0, 0, 0, 0, 0, 0. So this is the balancing factor. Here, the balancing factor is 1. Here, -1. Here, it's 0. Okay, here the balancing factor is -1, and it's for the 70, it's -2 here. It's imbalanced on the 70, right? It's already imbalanced on the 70. So now it's 1, 2, 3. So let's assume that right now 90 is not here. 90 is not here. Because we are trying to do some insertion. Let's assume that 90 is not here right now. Okay, so for here it is 0, it is -1 here, and 1, 2, 1, 2, 1, 2. So it's 0 here. 30, 20, it's 1 here actually. 1 here. 1, 2, 3, 1, 2. Okay, so it's 1. The right height is 2, the left height is 3. That is why 1 here. So for here it's 0, here it's -1, here it's 0, here it's -1, here it's 1, and the left height is 1, 2, 3, and right height is 1, 2, 3. So it's 0 here, -1 here, -1 here, and here it's -1. 1, 2, 1, 2, 3. So it's -1 here. Here it's 1, 2, 3, 4, 1, 2, 3, 4. So it's 0 here. And height of the right is 1, 2, 3, 4, 5. Left is 1, 2, 3, 4. So it's -1 here. So now you can see it's balanced. Now I want to insert 108. Okay. So if tree is balanced, what is the effort to find out 108 position? What is the effort? It is order of log n. In binary tree, it was order of n. Why? Order of n. Why? It could be skewed. It could be skewed like this, right? But we know that in Avl tree, skewed tree is not possible. Skewed tree is not possible. Okay, we know that. So that is why it's order of log n. It's balanced means on the left side and the right side, the height is almost same. The height is almost same. So if you want to insert 108, where can be it inserted? It can be inserted here. This is the right position. Okay, we will go on the right of 100 because 108 greater than 100. It's less than 200. That's why we'll go on the left. Less than 150, less than 120. Okay, less than 10, greater than 105. So we'll insert 108 here. Now let's redraw the balance factor. Here the balance factor is -1. Okay, here the balance factor is 1. Here the balance factor is 1. Here the balance will be 1, 2, 3, 4, 5, 1, 2, 3. Here the balance factor will become at this position. It's 1, 2, 3. 1, 2, 3, 4. Here the balance factor will become 1. Here also the balance factor will become 1. Okay. Instead of 0, it will become 1. Now at 100, at root, the balance factor will become what? -2. Because the height of right subtree is 1, 2, 3, 4, 5, and 6. Height of left subtree, what is the height? It is the maximum distance from any leaf node. Maximum distance from any leaf node. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 leaf nodes. But 108 is at the maximum distance. So that is the height. So what is the left subtree height? It is 1, 2, 3, and 4. It is 4 and 6 here. That is why it's -2. Now it's imbalanced at 100. It's imbalanced at 100. Right? So how to make it balanced? Now that subtree concept, the ABCD that I've written, this will come into the picture. Okay, so for rotation, we are not going to write down the whole tree again and again for rotation purpose. So the second task we need to identify is, where is it imbalanced? Is it LL, or is it LR, RR, or RL? Okay. Pause the video and try to find out which one of the following problem: LL, RR, RL, and LR. Which one of these 4 occurs here? Pause the video and try to find out. Now, as per me, this is RL. Why RL? Why RL? This is RL. Because the height of the tree is coming, this -2. This -2 is coming from where? From where is it coming? It's coming from the right subtree, right? Right subtree. See, this node, this connection is contributing more. It's saying that height of the right subtree is 6 here. It's 6. And from where is it coming again? From this connection, It's 5 from here. Right now, if you calculate the height of this part, it is 1, 2, 3, and 4. So here the height is 4, here the height is 5. So that is why this connection contributed in the height, not this connection. That is why we need to balance out this thing. So let's take 100, 200, and 150, and rest other thing as okay. I need to make it more clear for you guys to understand it. We will give them some generic label because that won't be a part of solution, or you can say that won't be taking any part in our problem. So we will consider 100, 200, and 150. Rest we will label them. We label this thing as A. This whole subtree we label at A. Label as A. Okay. This whole subtree we will label as, we will label this subtree as B. We label this subtree as C. Okay. Now we will try to solve the problem. So this is the case. Okay. I'm making some mistake here. Okay, let me use some other color. So for 150, we have to take two children, right? For 200, we have one children only, and here we have 150. So we'll take two children, one this children, and one this subtree. So we will label them B and D. Okay, B and D. So our tree we can draw like 100 A. Okay, 100, 200, 150. It's, what is the problem? It is RL. So that is why we will apply right rotation here first. Right rotation here first, right? After right rotation, it will look like 100, 150, and 200. Okay, it will look like this. Then we will do, it's RR now. We will do left rotation on 150. So 150 will become the root, 100 will come here, and 200 will come here. Now let's talk about the children. We may label them as A here, D here, B here, and here we label it as C. These are the subtree, A, D, B, C. These are the subtrees, okay? This green one, this one is D. This whole subtree is D. So we are not going to touch the structure of the subtree. We will just change its parent if required. This is C and this is A, okay? Now, after this rotation, what is the structure now? Here, the left one will remain same, B. This will become B, and this will, C will remain at the same position. After rotation, once 150 will become the root, 100 will have two children, A and D. B and C will remain at the same position. Now, using this solution, let's again try to write down the whole tree, right? I want to make it some more clean, right? Okay. So that is why I will write down this whole 150 tree again here. So that you would know that what is A, what is B, what is C, and what is D. We have 120 here, 170 here. Here we have 110, 130, 140, 105, 115, 160, 180, 166. Okay. Now this is D. This is B. Okay. So once we did the algorithm, the balancing algorithm for RL problem, this is RL problem, right? For RL problem, we created the tree like this, right? Okay, I'm sorry. This is 100. On the left side, we have A. On the 100, we have left side A. A is this subtree, right? A is this subtree. I just labeled this subtree because we don't have to consider the whole subtree. It is very difficult to show the rotation if I write down the whole subtree here, right? Then C is the right child of 200. Okay. D and B are the children of 150, left and right children respectively. After construction, we come to this conclusion: 150, 100, and 200, A, D, B, C. A, D, B, C, right? A, D, B, C. So our tree will look like this. After construction, it will look like 150. Okay, yes, let me use some other 100 and 200 here. After that, we have ADBC here, ADBC. So what is A? A is this whole subtree. What is this whole subtree? This is 50, 30, 70, 80, 20, 10. After that, we have 40, 45. 40, 45. So this is A. Okay, A. After that, 100 have a children D. So now what's happening here is this D was the left child of 150 and we made it right child of 100. We made it right child of 100. Okay, right child of 100, which is 150. Sorry, not 150. 120. 120, 110, 130, 140, 105, 115, and the newly inserted node will after the shuffling of the children on the rotation, the newly inserted node will come here. Okay, so the Avl insertion is not that easy as binary search tree, because after inserting at the leaf level, or you can say at the bottom level, we have to make the rotation to make the tree balanced again. Okay, and what are the child of 200? It's B and what is B? This is B. B and C. B and C, right? What is B? B is 170, 160, 166, 180. And here we have 220, 215, 225, 230. And you can check that this tree is balanced. Okay. So let me label them again. So this whole subtree is A. This whole subtree is D, right? It's D. This whole subtree was basically, we named it as B, and this is C. So after one insertion, this much we have to do. And it is easier if you identify the 3 nodes which will be the part of the rotation, and rest other nodes you can make as the subtree and label them. See how easy it is. Once I label this whole subtree as A, okay, because it was difficult to carry this A, B, C, D, this subtree in the rotation algorithm. It was very difficult, right? But if I label them and later, like I circled them, right? I labeled this, and I checked that at the end of the algorithm, this A will be the left subtree of 100, and I made it so. Okay, this is how rotation can happen. So thank you all for joining today, and this is it for Avl tree. We have seen the insertion. The deletion is same as binary search tree, where once we delete the node, we replace it with predecessor or successor. We will check if imbalancing is happening. Wherever the imbalancing is happening, we apply this rotation algorithm. Okay. And if time allows me, I will basically make some more, create some more example on this Avl tree and try to explain you the insertion, deletion, and creation of the tree. I will do few examples, like 2-3 examples on this. Thank you all for joining, and see you in the next lecture.